Hey guys, thank you for coming back to us. This is our third week. So in this lecture, let me finish the previous node embedding lecture. So we have talked about the matrix vectorization perspective toward the existing network embedding methods. So in the previous lecture, we have talked about deep work in node-back, right? So we shortly talked about how the deep work in node-back could be connected to the matrix vectorization. So I got some comments from students. It was too fast to understand the essentials, so I prepared a little bit more explanations about this idea. So let's focus on one of the embeddings. So debug is the simplest embedding, right? So it is composed of the several functions and the representation. So we have a logarithm, right? And then volume, B and T, and some adjacency related terminologies. So let's go to the detail. So first of all, so A is just adjacency matrix, right? So it corresponds to this, right? The two-dimensional matrix, and D is just degree matrix, right? So degree matrix is just composed of the diagonal matrix and diagonal entities. All others are composed of zeros, and depending on the degree of each node, some scores are here, right? For example, the node A is connected to two other nodes. It has two, right? 5, something like that. So it is degree matrix. We have the inverse computation of the degree matrix, and we can compute this, right? And with this matrix computation, we can get this, right? And thus T is the window size, right? The window size is coming from the random walk, right? So to consider the context for the encoding the target node, and we set the specific window size as a parameter, right? It depends on the neighbor size. So it is the predefined parameter. And we sums up and normalize by the T. And the volume is just simple summation of all of the varied numbers in the adjacency, right? Except the zero value, we just count all the non-zero values from the A. It is gonna be volume, right? And B is just number of samples, number of negative samples. It basically assumes that we use negative sampling, right? So I believe now you are able to see how to compute this. We have some matrix, right? It is gonna be still two-dimensional. So dimension-wise, it is still following this, right? We have the V by V matrix as an output of this matrix, right? So from this, we have to compute this for network embedding. So theoretically, it is gonna be same as the network embedding, the deep work embedding. So for your information about the rank D approximation by SVD, so we computed, for example, the M. So we got the M from this, right? So from the M, we have to decompose using SVD, but we give the specific the rank D, right, for approximation. So let me recall your memory for the rank K approximation. So basically it's a singular value decomposition we call SVD. It is our input matrix. We try to decompose into 3 matrix computation. So dimension wise, so originally it follows n by n, and then we have the left singular vector as n by n, and right singular vector the n by n, and the eigenvalue matrix we have the n by n. So in this case, the rows of Vt are eigenvectors of the dt d. So just following the definition, and actually you can prove what the means of this sentence. And this is a diagonal matrix, and each element in the diagonal matrix and corresponds to the eigenvalue. The rows of U are coefficients for the basis functions in V. We also assume that M is larger than N. The rank D is N. So it is before the approximation. We also call to the approximation the as dimension reduction. So this is the rank D approximation. So in this case, the rank is N, the same as the rank of the column, right? So for example, it is our input, and we decompose into the U and sigma and V, right? Something like this. It is diagonal matrix, right? The rank is 3, right? So yeah, just read the sentences here, and we reorder the eigenvalue, and the order of the eigenvector is also adjusted. And to get the approximation, so currently our target dimensionality, the target rank is K. Currently K is smaller than N, right? We just choose the first K eigenvectors, and for the U, and we also take the K largest eigenvalues from the sigma, and we also get the reduced the matrix from the Vt. So for example, in this example, when we use just K equals 2, K is equals to, and then we take for the U, we take just this, the sigma we take this, and for V we take this, and this is the rank k approximation. So this k should be the same as the size of the representation for the debug, right? Previously we have the input graph. We reduce the dimensionality for the v, right? This was v, and this was k, right? Each node has the k number of the floating value for the latent representation, right? So that's why we have this, and it will be, we expect theoretically the same as this one. I'm sorry, this embedding. So any questions about this? Let me know. Right. So with this way, we can get the theoretical approximation from this. With this way, we can get the theoretical relationship between the different embeddings and across the matrix vectorization in this schistogram based embeddings. Alright, so today's lecture's topic is the PageRank. It is really important these days as well. So in the early of the last 10 years, so in the beginning of the, maybe, I don't know, when the Google established the company, so anyway 2000, so between 2010, the PageRank was really popular in their search engine, and even in the many machine learning systems, so natural language processing, and the graph mining, and in many areas. So still, this is one of the important topics in the graph mining as well. So that's why we need to understand pretty well about this topic. So let me ask you a question. So how do you rank the node by using node importance? So could you estimate the node importance in this graph? How would you do that? So maybe you just consider the number of links for the 5. For example, it has 4 edges, right? And we might say the one has 2 edges, so it looks like 5 is more important than the node 1, right? We can also think about that, do we have to consider the in or out links? So for example, 5 has 3 incoming link, and it has 1 out link, right? Is that matters for deciding node importance? So what do you think? So in this lecture, we try to define the way to decide the most important nodes. So one of the methods. So depending on the measures, so you have multiple ways to estimate the node importance. But we will just give you one specific way for getting the node importance, and using the score you can rank the nodes in the graph. So when is it useful? So you can get a social influence, right? Maybe we have so many influencers these days, right? The YouTube and Instagram, you can sort the influencers using some node importance, right? Also, you can get the website ranking, or when you have some Facebook like a web service, so you can recommend the future friend by using the node importance, or you can predict the future link using link prediction, right? You have multiple ways for that. Oh, the same slide was here. So one way to do that is called the page rank. So today's learning objective. So the page rank algorithm finds a probability distribution used to represent the likelihood the person randomly clicking on links will arrive at any particular page. So basically it is to find the probability distribution, which is about the clicking, the likelihood. So we will come back here again. So we have important assumptions for the algorithms. So they think link is a kind of vote. So you know what the vote means, right? To elect the president, right? And we have to give our the vote to the candidate, right? So like that, like the vote in presidential election. So sending link could be considered as kind of the vote to the web page, for example. It could be person, right? You give your hyperlink to a web page, and the web page got a vote from you, right? So it's similar to the presidential election. So when the person has more votes, is likely to be elected, right, as the president, right? So the pages or people have more incoming links are more important. So it is one of the important assumptions in the PageRank. And at the same time, the links from important pages are more important. So we can't that links more. That links more. So different from our presidential election. So we think all the votes equal, right? That is from the basic law. So our law, we also call the 헌법 in Korean. So the fundamental law, I'm not sure how to call the law in English. Anyway, the law says the vote from all people considered as the same, right? So we don't have some important vote or not important vote, but at least in the web pages or the social media, in particularly for the PageRank things, so we have some important pages. So for example, Justin Bieber follows a person, and myself. So Hogan Park follows a person, some other person. So who is more important? So obviously, so Justin Bieber's the friend is likely to be more important, unfortunately, right? It's likely to be popular from other people, right? Likely to click that person or watch the person way more, right? So we have important pages. We also consider the number of the links as well. We consider the both concepts, so both assumptions. So these are assumptions, and that's all. That's all, and that is the almost everything about the PageRank. And we just formulate some assumptions mathematically. So